Okay, students, in this video, we are going to discuss about velocity selector or velocity filter. Then we are going to discuss about the connection between epsilon 0 and mu 0. Then after that, we will discuss about the force acting over a current carrying conductor which is placed in an external magnetic field. Okay, therefore, let's start. Initially, we have to speak about velocity selector or velocity filter. For speaking about velocity selector or velocity filter, let me have a magnetic field like this. The magnetic field is inverse. Okay. Then, if I am trying to throw a positively charged particle, if I am throwing a positively charged particle with a velocity v in this particular direction, due to this cross mark as magnetic field, due to this magnetic field, this charged particle, it will experience a force. Can you say in which direction? For finding out the direction of force experienced by the positive charge particle moving in this direction, we will have to use our left hand, Fleming's left hand rule, in which forefinger should be placed in the direction of field, middle finger is placed in the direction of current, then thumb will experience the direction of force. Therefore, we can have a force in this direction, and I am denoting this force as FB. Let me denote this force as FB since it is the magnetic Lorentz force. Okay. Then due to this magnetic Lorentz force, there will be a deflection in the charge. Therefore, due to this magnetic field, the charge will get deflected in this fashion. Let me write it is deflection by magnetic field. Okay. In order to avoid this deflection, we have to create an electric field. In order to avoid this deflection, I'm going to create an electric field. For creating an electric field, let me place a charged sheet over here. Let this charged sheet be negatively charged sheet. We are placing a negative charge sheet over here and a positive charge sheet over here. A negative charge sheet and a positive charge sheet is placed. This is a positive charge sheet. A positive charge sheet is placed at the upper region and a negative charge sheet is placed in the lower region. Due to this charge sheet, there will be a uniform electric field created, and the direction of that uniform electric field will be from positive to negative. Therefore, this is the direction of the uniform electric field created. Due to this electric field, the charge particle, it will experience a force. The charge particle will experience an electrostatic force, and that electrostatic force will be downwards, and we'll call this as Fe since it is electrostatic force. The electrostatic force experienced by the charge particle is downwards, and due to this electrostatic force alone, if we are neglecting or if we are forgetting about the magnetic force acting over it, due to this electrostatic force alone, there will be a deflection by electric field like this. Deflection by electric field like this. Then the magnetic Lorentz force will try to move it upwards. The electric Lorentz force will try to move it downwards. Initially, the charge particle was moving with the velocity v. There will be a situation where net upward force will become equal to net downward force. You imagine that situation. If the net upward force, that is FB, is equal to the net downward force, then what will happen? If magnetic Lorentz force is equal to electric Lorentz force, we could write magnetic Lorentz force as QVB sine theta. In this case, the theta value, velocity and magnetic field are perpendicular, therefore sine 90. is equal to, as we know, electric Lorentz force is QE. QVB sin theta is equal to QE. Q will get cancelled. Sin 90 is 1. Therefore, we will get V is equal to E by B. What's V? V is velocity. And we are getting an expression for velocity as E by B. At velocity equal to E by B situation, or if the velocity is becoming equal to E by B, then FB will be equal to FB will be equal to FE, and in this situation, the charge particle will not experience any force. The net force experiencing over this charge particle will be 0. Therefore, the charge particle will move undeviated. The charge particle will move undeviated. Let's analyze the situation again. If the velocity is becoming equal to E by B, FB will be equal to FE, and in that situation, the net force acting over the charge particle is 0. Therefore, the charge particle will move without any deviation. That is, it will move with that velocity V in this direction itself. This velocity is called velocity selector. This velocity, it is called velocity selector. It is the velocity in which a charge particle will move undeviated if a mutually perpendicular electric and magnetic field is applied. If a mutually perpendicular electric and magnetic field is applied, the velocity with which the charge particle will move undeviated, that velocity V is equal to E by B, it is called as velocity selector or velocity filter. Hope you have understood velocity selector and velocity filter. Then we'll speak about the relation between epsilon 0 and mu 0. Let us speak about the relation between epsilon 0 and mu 0. For that, I'm taking a new slide. For speaking about the relation between epsilon 0 and mu 0, can you recall the expression for 1 by 4 pi epsilon 0? What's the value of 1 by 4 pi epsilon 0? It was 9 into 10 raised to 9. We have learned it in our first chapter. And can you give me the value of mu 0 by 4 pi? In our Biot-Savart's law, we have learned the value of mu 0 by 4 pi. The value of mu 0 by 4 pi is 10 raised to minus 7. Hope you can recall these two. Then let's take this equation as our equation number 1, and let's take this equation as our equation number 2. 1 divided by 2 will give 1 divided by 2 means 1 by 4 pi epsilon 0 divided by 2 means we can multiply the reciprocal. That is 4 pi by mu 0 is equal to 1 divided by 2 means 9 into 10 raised to 9 divided by 10 raised to minus 7. In this case, we could cancel this 4 pi and 4 pi. Then it will be 1 by epsilon 0 mu 0 is equal to 9 into 10 raised to minus 7 will go to the numerator and it will become 10 raised to 9 plus 7. That is 10 raised to 16. 10 raised to 16, it can be rewritten as 3 into 10 raised to 8 the whole square. You just analyze 3 square is 9, 10 raised to 8 whole square is 10 raised to 16. Therefore, 1 by epsilon 0 mu 0 is equal to 3 into 10 raised to 8 the whole square. Can you connect 3 into 10 raised to 8 with some constant? Yes. C, speed of light in vacuum is 3 into 10 raised to 8. You know, the speed of light in vacuum is 3 into 10 raised to 8. Therefore, 1 by epsilon 0 mu 0, it is C square. 1 by epsilon 0 mu 0, it is C square, or C is equal to 1 by root of epsilon 0 mu 0. This is the relation between epsilon 0 and mu 0. This is the relation between permittivity and permeability. The relation between permittivity and permeability is 1 by epsilon 0 mu 0 is equal to c square. Okay, this is the relation between permittivity and permeability. Then now let's move on to the next topic, that is we are going to discuss about the force acting over a current carrying conductor which is placed in an external magnetic field. Assume we are having a current carrying conductor, force acting over a current carrying conductor which is placed in an external magnetic field. For speaking about force acting over a current carrying conductor which is placed in an external magnetic field, let us assume that we are having a current carrying conductor like this. Let the length of the current carrying conductor be L and the cross-sectional area be A. L is the length of the current carrying conductor, A is the cross-sectional area. Then this current carrying conductor, it is placed in an external magnetic field like this. The current carrying conductor is placed in an external magnetic field like this. In this current carrying conductor, there is a current passing in this direction. This is the direction of current, and current and magnetic field, they are making an angle theta. The current carrying conductor is consisting of free electrons, and the free electron density of the current carrying conductor is small. What was free electron density? We have learned free electron density in our current electricity chapter. It was the number of free electrons in a unit volume. Number of free electrons in a unit volume. Okay, then we have to find out the force acting over this current carrying conductor which is placed in an external magnetic field. In order to find out the force acting over the current carrying conductor which is placed in an external magnetic field, let us recall the expression for force acting over a charge particle which is placed in an external magnetic field, or force acting over a charge particle which is moving in an external magnetic field. The force acting over a charge particle which is moving in an external magnetic field, it was QVB sine theta. Hope you can record this. F is equal to QVB sine theta. It is the force acting over the charge particle which is moving in an external magnetic field. Then in this case, if you are using this relation, instead of this V, we can say instead of V in this situation, we could use VD. Can you recall what is VD? Yes, VD is the drift velocity. Average velocity attained by the free electron was the drift velocity, and V is drift velocity. In this situation, we could replace V as drift velocity since electrons are moving. Then in this case, if you are able to find out the value of Q, you could substitute the total charge flowing. If you are able to find out the value of the total charge flowing, you could easily substitute the value of total charge and you could get the final answer. In order to find out the total charge and substitute, let's find out the volume of this conductor. What should be the volume of this conductor? Yes, volume is area of cross section into length. This is the volume of the conductor. What was small n? Small n was free electron density. What was free electron density? It was the number of free electrons in a unit volume. Number of free electrons in a unit volume. Therefore, if you know the number of free electrons in a unit volume, you could find out the number of electrons in the total volume. The total number of electrons in volume, it should be free electron density into volume. Free electron density into volume means it is NaL. NaL will be the total number of electrons in this volume. Total number of electrons in this volume. And if we know the total number of electrons in this volume, you could find out the total charge of electrons in this volume. Therefore, total charge of electrons in that particular volume, that is actually Q, which we want to determine over here. Q, it should be what's charge of one single electron? The charge of one single electron is E, small letter E. Therefore, the total charge of the electrons in this volume will be E N Al. Since this is the number of electrons in that volume, if we are multiplying it with E, we will get the total charge of electrons flowing. If we have found out the total charge of electrons flowing, you could substitute the value of V as Vd and the total charge of electrons flowing as EnAl. If we are substituting these two values in the expression for F, we could write F is equal to Q can be replaced as EnAl. Q can be replaced as EnAl. Then V can be replaced as Vd. Then write that B sin theta as such, B sin theta. Then we will have to recall an expression for current in terms of drift velocity. What was the expression for current in terms of drift velocity? It was I is equal to NAVDE. We have learned an expression like this in our current density chapter. I is equal to NAVDE. I is equal to NAVDE. NAVDE. Instead of this NAVDE, we could substitute I. Therefore, we will get F is equal to ILB sin theta, and we could write it as F is equal to I into L cross B. If we require, we could write it as F is equal to I into L cross B, where F is a vector quantity, L is a vector in the direction of current, and B is also a vector. The L is a vector which is in the direction of current. Since I is a scalar quantity, we are using I into L cross B. Okay. Or F is equal to ILB sin theta. What is the force acting over a current carrying conductor which is placed in an external magnetic field? It is F is equal to ILB sin theta. Then you should remember one more expression, that is the expression for force per unit length. Force per unit length. What is force per unit length? It is the force acting over a unit length of conductor. We could obtain the expression for force per unit length by dividing total force with the total length. Dividing total force with total length. Then you could get the expression for force per unit length as total force. What is total force? The total force is ILB sin theta divided by L. Therefore, force per unit length will be IB sin theta. Okay, this is the expression for force per unit length. The SI unit of force is Newton, that we know, and the SI unit of force per unit length, it is not Newton, it is Newton per meter. Remember this. Okay, therefore now we are having force acting over a current carrying conductor which is placed in an external magnetic field. Hope you have understood this. We are stopping our video right over here.